All right, so for this next section, we're going to be talking about section 6.5, integrating with U substitution. So now we're starting to lead into a few more advanced integrating techniques, and it's not just power rule, like we did in the previous sections, but this video might be a little bit longer simply because I do recognize the importance of U substitution, and anytime you think of a calculus test, and if there's some kind of integration problem in there, I would say maybe 7 times out of 10, there's going to be some kind of U substitution involved. It's a very popular integration technique, so I definitely think it's worth me going over all of these problems in details. And you guys will even notice that the problem set is a little bit hefty, 24 problems. So I just want to make sure that we are as sharp as possible in this topic, and really it's going to be that way for the other integration techniques as well. So as far as integrating with U substitution, you can already kind of tell right now that these are types of problems where you can't necessarily do the power rule to answer them. There's a lot more complicated than that. All right, but a way to make these problems a lot easier to work with, and a lot of times to where you can even use the power rule, is by using U substitution. So essentially what you have to do with U substitution, and I kind of put just a few steps to kind of keep into account. Look for a piece of the function whose derivative is also in the function. If you're not sure what to use, try the denominator or something being raised to a power. This isn't always true, but a lot of times, whenever you see anything like in a denominator, or maybe if you see anything, not this one, but or if you see something in an exponent, a lot of times, not always, but a lot of times those are going to be the ones that you're going to use as your U. Okay, so I don't know why it's so blurry. Okay, hopefully that focused it a little bit better. All right. So then once you do that, you're going to set U equal to that piece of the function and take the derivative with respect to the variable. Okay, so and the other thing too, that you have to keep in mind, when you take the derivative, you're going to multiply it by dx, and then you're going to use your U and du expressions to replace parts of the original integral, and your new integral will be much easier to solve. So let me just kind of show you guys exactly. So we can't necessarily do the power rule here because we're not dealing with a single variable raised to a power, but we can kind of make this turn this into a single variable by using U substitution. So the way we're going to do it is every teacher has their way of doing it. This is how my Calc 2 professor did it, so I kind of like doing it how he does it. So you're going to kind of use a fancy bracket, and you're going to go ahead and I'm going to make the inside of my function my U. All right, and I'll tell you right now, that's half of the battle, is deciding which part of your integral you're going to set as your U. The reason why I'm doing this is because there's really no outside variable or anything on the outside. So if I said this is my U, and I kind of have to think ahead and think about what the derivative is. Well, the derivative is just 3, right? The derivative, that's just going to be 3, and then we're going to multiply it by dx. The thing is, the ultimate goal here is when I get dx by itself over here, so if I divide both sides by 3, when I substitute everything back into my original integral, there cannot be a single x variable. Everything has to be in terms of U. The second you have any kind of x variable in there, you've already done it wrong. You should probably pick a different U. All right, so I'm going to go ahead and substitute everything that I can. So right now I know that this is U, so I'm going to rewrite this as the integral of U to the 5th power. dx is going to be du over 3. Now, this is a much easier problem than most, but in here, nothing really canceled out, so we're good. As long as everything I have is U, either U or constants, then we're good to go. And then what I always like to do is any constants that I have, I always write outside of the integral. So here I have like a 1/3 there, so I'm going to write 1/3 times the integral of U to the 5th du. Okay, now this is a much easier problem to work with. I could just go ahead and do the power rule because this is just a basic integration technique. So that's going to be equal to 1/3 times U to the 6th over 6, right? And so when I multiply across, that's going to end up being plus C. Never forget that. And then when I multiply across, it's going to be U to the 6th. The thing is, now when for my final answer, I'm going to bring back my U into my function. And it's going to be 3x minus 4, and I'm going to raise that to the power of 6. Divided by 3 times 6 is 18 plus C. Okay? So there is the worked out version of that problem, and that's the final answer. Don't forget plus C. Anyways, now this is kind of a more typical example of a U substitution. Here, I have to make sure that I look for a piece of my function where the derivative will end up equaling something, where I take the derivative of that function, and then it's going to look very similar to a derivative of some other part of the function. So if I look here, I'm kind of looking ahead. I know x cubed plus 7. I know that if I took the derivative of this little portion, then I'll have a 3x squared somewhere, and here I kind of have a 6x squared, so that's pretty close, right? So what I'm going to do, I'm going to set my u equal to x cubed plus 7, okay? Then when I take my derivative, so du, that's going to be 3x squared times dx. Now, here's the thing. It's not, my derivative isn't exactly 6x squared, but as long as if there's only a difference in a constant, then we're fine, okay? What matters is that the power is the same, and, we can do substitution. Now, some people like to say, oh, well, I can go ahead and just multiply maybe both sides by 2 or whatever. I just tell everyone the easiest way to do this is get dx by itself, or at least this is what I think is the easiest way. So we're going to get dx by itself by dividing both sides by 3x squared. And now we're going to go ahead and do all of our substitutions into the original integral. So I have 6x squared there. I can't really substitute anything into that, so I'm going to leave it as that, 6x squared. Then I have x cubed plus 7 to the 8th power. So I know that x cubed plus 7 we established as u, so I'm going to write that as u to the 8th power instead. And then dx is equal to du over 3x squared, so I'm just going to write that in there, du over 3x squared. Now again, I said that our goal is to always make sure that everything in our new integral is in terms of u. See these x squares? Well, they better cancel out. And they do, luckily. So if they don't, if they don't cancel out, then you probably picked the wrong u and you should start this problem over again. So anyways, now that we canceled out our x squares, I have 6. Now I always like to take out my constant. So I have 6 divided by 3, which is going to be 2 outside of the integral. And then I have u to the 8th du, right? And now we just do our simple power rule, all right? So this is going to be 2u, and then raise that to the 9th power, all divided by 9, plus c. All right, now you usually don't want to leave your answer in terms of u, so I'm going to go ahead and plug the, substitute back in our x cubed plus 7. So now our final answer is 2x cubed plus 7 to the 9th power, divided by 9, all of that plus c. Okay. All right, let's go on to the next problem. All right, so this is another kind of basic one like the one above it where I don't really have any outside functions or, I guess like, any outside expressions to work with. But if I took the derivative of that inside, then I can't, it'll just be a constant, and, I can always take a constant out. So with this one, my u that I'm going to set is going to be whatever's on the inside, 4x minus 5. And then du is going to be 4 times dx. And like I said, always try to get dx by itself. So I'm going to have dx is equal to du over 4. And so when I do all my substitutions, I'm going to be left with the integral of, let's see, it's going to be the square root of u, but I'll just write that as u to the 1/2. And then dx is du over 4. All right. So we're good there. Again, I always take my constants out. It's just a habit I've always built. 1/4 times the integral of u to the 1/2 du. So now if I go ahead and do my power rule there, I'm going to add 1 to that, or 2 over 2. So that's going to be u to the 3/2. And then times, divided by 3/2 is the same as multiplying by 2/3. And I can't forget that 1/4 here either. So all of that plus c. And so now I can rewrite this as, I know the 2 and the 4 cancel to become 1 over 2, or reduce down to 1 over 2. And so I'm going to rewrite this as 4x minus 5 to the 3/2 power divided by 2 over 3 is 6 plus c. Okay? Or you can write that as 1/6 times all of that, whatever floats your boat. Okay. So now this one's a little bit trickier. So if I have to decide what u value I'm going to use, let's see. I have to think about this. I'm starting to think ahead. Some people might say, I know that sometimes I said like, oh, maybe set the denominator equal to your u. And I mean, that might make a little bit of sense. You know, you can try to work it out. I don't know if I should work it out. Maybe I will. Maybe I'll do that real quick. I'll just do it quickly over here. If I set my denominator equal to u, right, I'll have u is equal to the square root of x, right? And I do du is equal to 1/2 x to the negative 1/2 power dx, right? That's the same thing as du is equal to 1/2 square root of x dx. And if I get dx by itself, I multiply both sides by 2 square root of x. So that's 2 square root of x du is equal to dx. Then if I did all of my substitutions back into the original, I'm going to have the integral of square root of x minus 1 squared divided by u times, and then dx is now 2 square root of x du, right? Did I accomplish my goal here of getting rid of all the x values? I mean, here's the thing. I can expand this out and it'll multiply. There's nothing that canceled out. I still have x terms in my integral. So this is definitely not the way to go. All right, and that's going to happen sometimes. And yes, it's going to be frustrating that you did some work and you did some stuff and that you chose the wrong u, but you know, that's just the reality of calculus. Not everything's going to go perfectly the first time around. You can try to, and you'll get better at them, better at noticing the patterns when you work out these problems. But here's the thing. It's kind of nice because I did notice, but do notice that when I took this, the derivative of square root of x, I did end up with 1 over square root of x. And don't I kind of have a 1 over square root of x there? So it might actually be worth it to set this part of my integral equal to my u. So I'm going to do the square root of x minus 1, and you'll see what happens. So if I take the du, well, I already did it. I already did the work. So I'm going to just say that that's equal to 1/2 square root of x, and then that's just 0. So 1/2 square root of x dx, right? So then to get dx by itself, I just multiply both sides by 2 square root of x times du. All right, and now I'm going to go ahead and do all my substitutions. So when I do all my substitutions, I'm going to have the integral. I already said that that was u, so I'm going to write that as u squared divided by the square root of x. And now notice that if I multiply by dx is now 2 square root of x du, well, my square root of x cancels. And now I've accomplished that goal of not having any more x terms in my integral. So I'm going to bring my 2 outside of my integral, and then I have u squared du. And again, this is just a very simple power rule. So I'm going to go ahead and that's going to be 2u cubed over 3 plus c. And then I can substitute this back in there. So that'll be 2 parentheses square root of x minus 1 cubed over 3 and all of that plus c. All right. So not too bad. And again, some trial and error, but that's expected to happen. And I hope you guys understand that. So let's kind of move up a little bit. Sorry. So now I have this one. So again, you have to be strategic with how you pick your u value. I'm going to pick my u to where if I took the derivative of something, it'll equal, it'll be the same as some other part of the function. So my u, and in this case, it's the exponent, and that's going to happen a lot. So if I chose cosine of x as my u, well, let's see how it works out. If I do du is equal to cosine is negative sine of x dx. If I got dx by itself and I divided both sides by negative sine of x, that's going to be du over negative sine of x. And now I'm going to go ahead and do my substitution into my integral. So it's going to become the integral of sine of x, e to the cosine of x we said was u, and then dx we said is du over negative sine of x. And good thing, the sine of x is canceled, and now all I have to worry about is the integral of e to the u times du, right? And the integral of e to the u, hopefully you remember from those integral rules or those basic integral rules from the past. We're just going to go ahead and the integral of e to the u is just going to be, well, e to the u plus c, right? And we went ahead and we're going to go ahead and do our substitutions. And u was cosine, so it's going to be e to the cosine of x. Oh, wait, there's something going on here. Oh, yeah, that's right. The negative here, I should have put outside, so that's negative, sorry. So it's negative e to the cosine of x plus c. All right. let's keep going. Now this is where this is going to be probably the problem that'll have everyone's head explode. This is one where and I'm throwing this problem in there because I have seen a lot of professors throw this problem to see if kids can recognize what to do and if kids remember their trig identities. Right off the bat, this is not, you can't immediately know what your U value is going to be. There's going to be a lot of manipulation that you have to do with this problem in order to make it work. I'm definitely going to include a problem like this on the test, just a heads up, because I really want to make sure that you guys are aware of what to do. Don't freak out when you see a problem like this. But you'll notice right now, just right off the bat, I can't determine what value of U is going to equal any part of the outside function. I mean, sure, if I can X, but that's not going to accomplish anything if you want to work out the problem. So what we're gonna have to end up doing here is we're gonna have to rewrite this as the integral of cosine squared of x times cosine of x dx, right? For those of you who weren't strong in pre-calculus, or especially that section on trig identities, we'll get through this together, I promise. All right. So one of the things you should remember is that sine squared of x plus cosine squared of x is equal to 1. So if I want to know what cosine squared of x is, I can rewrite cosine squared of x is equal to 1 minus sine squared of x, right? And then I can get this and substitute it into cosine squared of x. So that's what I'm going to do. So I'm going to rewrite this as the integral of 1 minus sine squared of x times cosine of x dx. Okay? So now that I kind of rewrote my integral like this, is there something I can choose as my u that'll end up equaling some outside portion? Well, I know that if I took the derivative of sine of x, right, not necessarily sine squared of x, but sine of x, that will give me cosine of x on the outside. So I'm going to go ahead and give that a shot, all right? So I'm going to say u equal to sine of x. Right, and here's the thing, like some people might be inclined to take the derivative of u, set this as my u. And just to sort of prove you wrong, if I set that as my u, 1 minus sine squared of x, right? Well, just think ahead. If I just kind of did my du, and you know, you'll get to the point where you'll be able to think ahead for a lot of these problems. But if you have to work it out, by all means, go for it. That'll just kind of be chain rule where I bring, you know, this is like saying sine of x squared, so that'll be minus 2 with the negative there. Minus 2 sine of x times cosine of x, and then dx. And then, I mean, that, again, that doesn't really help you accomplish anything. If you try to do any substitutions back, you're still going to end up with x terms. So, you know, I've done problems like these so many times, so I already recognize that my u is going to be sine of x. So when I do that, my du is going to be cosine of x dx, right? And then if I get dx by itself, that'll be du over cosine of x. And so now if I go ahead and do all of my substitutions back into the integral, that's going to be equal to the integral of 1 minus u squared, right? Because we said u is sine of x and sine squared is u squared. And then times cosine of x times, we know dx now is du over cosine of x, and there you go. No, I missed it. And there you go. The cosine of x is canceled out, and now we have no more x terms in our integral, and that's what we were trying to do. So that's equal to 1 minus u squared du, and now the problem is just easy, right? We just do general power rule for integration for this. So the integral of 1 is u, integral of that is plus u cubed over 3 plus c, all right? And now we got to go ahead and get our u and plug it back in, so now we're just left with sine of x plus sine cubed of x divided by 3 plus c. All right, and prove it to yourself. If you took the derivative of this, you will end up with cosine cubed of x. I mean, if you want to. I don't think you will. But anyways, let's go ahead and move on to the next problem, or the last 4 problems in the back. This actually might not even be the longest video I've made. So anyways, ooh, this is another tricky one. So right off the bat, this doesn't, you know, and I think trig, I think I'm gonna have to talk to Nakarado and make sure that you guys really understand your trig identities, because this is definitely gonna bite you guys in the butt later. But yeah, so tangent of x. Again, there's nothing really obvious here that you can take the derivative of. So now you have to start thinking about it and say, is there something I can probably, can I change this in any way? Well, hopefully we remember that that tangent of x is essentially the integral of sine of x over cosine of x dx, right? And now over here, I can do something here. I know that if I took the derivative of sine of x, I would get cosine of x. If I took the derivative of cosine of x, I would get some version of sine of x, right? But again, you have to be strategic about it. And I'll show you the wrong way first on a separate sheet of paper, which you shouldn't write. But like some people might be inclined to make sine of x the u, right? Because if I said u is equal to sine of x, well, perfect. My du is cosine of x, which is somewhere else in there, right? But the problem is, if I were to do, if I got dx by itself and I got du over cosine of x, and then I did my substitution back into this, well, sure, I'll have the integral sine of x is u, cosine of x, and then cosine of x still stays there, but then dx is du over cosine of x. Well, I didn't cancel out my x terms. I'm going to end up with u over cosine squared of x, and what good is that going to do? How am I going to take the integral of that? So the best thing to do in this scenario is to go ahead and make your u equal to the denominator. And that's going to happen a lot. The denominator or exponents. I know my one example for, I think, the fourth one, that wasn't necessarily the case, but in a lot of times it will. All right, so if I take the derivative of that, it's going to be negative sine of x dx. And if I got dx by itself, I got du over negative sine of x. And so now when I do my substitute, that was ugly, but whatever. Now when I do my substitution again, I'm going to end up with the integral of, let's see, I couldn't really substitute anything to that, so it's still sine of x over cosine of x is u times du over negative sine of x, and voila. All my x terms canceled. The negative I'm going to bring outside of the integral, and that's 1 over u du. And as soon as you see 1 over u or 1 over x or 1 over or some constant over a single variable, the first thing that should come to mind is natural log. So we know that the integral of this is going to be negative natural log of u plus c. And then, of course, I'm going to substitute my u back in there, and I have negative natural log of cosine of x plus c. And that's my final answer. All right? Okay, so hopefully you're not too bored of this video, but because these next problems are a little bit different. You're still going to use U substitution, but now we have definite integrals. We have a lower bound and an upper bound to plug into this. And I already know what a lot of kids are going to do, and it's horrible, 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 horrible mistake. Well, let me just go over it. So first of all, I'm going to go ahead and do my U substitution like I normally would. Is there something in here that if I take the derivative of it, it's the same as some other part of the function? Yep. If I took the derivative of this inside, it will give me t squared somehow, or some version of t squared. So I'm going to go ahead and set my u equal to t cubed plus 1. And then my du is equal to 3t squared dt. Okay, I'm going to get dt by itself, and then I'm going to end up with du over 3t squared, right? Now, when I go ahead and I plug all of this back into my integral, I'm going to have, let's see, t squared times u squared, and then dt we said was du over 3t squared, right? And then the t squares canceled, and then I'm going to end up with the integral of u squared du, and then I can take out the 1/3 outside. Okay, but here's the thing. What are we going to do with those bounds? Okay, the thing is, these are the bounds for your t variable. Okay, these are not the bounds you're going to use for your u variable. Okay, now you can do the entire integration, and there is a way where you can still use these bounds, but that's only after you substitute things back in. That's how some teachers like to teach it. I personally think that's just too much extra work. I would rather you guys do your U substitution and plug in new bounds. So here's what we're going to do. We're going to have, so these are the bounds. It's not how you spell bounds, whatever. These are the bounds for your t variable. So we know that we have t equals 0 and t equals 1. But let's create the new bounds for your u variable. We know that u is t cubed plus 1. So for my t bound of 0, that's gonna be the same as a u bound of 0 plus 1 is 1. I don't know why I said 0, but anyways, all right. For my t bound of 1, I'm going to plug in 1 into t, and then my new u bound is going to be 2 for that one. So now my bounds are no longer going to be from 0 to 1. Instead, they're going to be from 1 to 2. From 1 to 2. Okay? And then when I do my U substitution, that's what those are the numbers that I plug in, and I'm good to go. So when I do my integral of this, I'm going to end up with 1/3 of u cubed over 3 from 1 to 2. Okay? And so what I'm going to do, I'm going to plug in, so it's going to be 1/3. I'm going to plug in my upper bound first. So that's going to be 2 cubed is 8 over 3. 1 cubed is, and then subtract it from the lower bound. So 1 cubed is 1 over 3. All right. And so this is the same thing as 1/3 times 7 over 3, which is 7 over 9. Okay. Now, I'm debating whether or not I should even explain this part. You know what? Why not? Because I know some people are going to be like, "But what about this way? What about the lower and upper?" What? So, one thing you could have done was not included your lower and upper bounds. And let's say you had the integral 1/3 integral of u squared du, right? One thing you could have done was you could have said, "Oh, well, that's the same thing as u cubed over 3 times 1/3 is u cubed over 9, right?" But then you could have rewritten that as, you could substitute your u back with your t variable, so that's t cubed plus 1 cubed over 9. And then you can use your lower and upper bound as what it originally was from 0 to 1. So we would use 0 to 1 in this case simply because now we're dealing with our t variable again. So we're going to use our t bound 0 to 1. I just feel like it's just extra work to this isn't as nice to look at or as nice to substitute values in as u cubed over 3. So I think it's much more worth your time to just change your bounds and then plug it back in, because this will give me the same answer. If I plugged in, 1 and 0 into this, I'll have, 1 plus 1 cubed over 9 minus 0 plus 1 cubed over 9, which is 2 cubed is 8 over 9. And this is minus 1 over 9, which is 7 over 9. You'll get the same answer if you do it this way, but I don't know. You pick the method you like more. I would recommend this one. I used to do it like this all throughout high school and even for the AP exam when I was in high school. But then when when I had my calculus 2 professor showed me this method, I never turned back. I love this method. So let's go ahead and let's do the other problem. So we have the integral from 0 to pi over 2 of cosine of x times the square root of sine of x. And okay, so I got to think, well, I have, and here's the other thing about U substitution. If you have like a function kind of like raised to a power or like, inside of a parentheses or whatever, usually what's inside of the parentheses is another good indicator that might be a good idea to use as U. Just throwing it out there. Again, there's no set rule and say, hey, this is always going to be your U. It's just something you kind of have to recognize, and that'll come mostly through practice. So I'm going to go ahead and set my U as sine of x. All right. I've only done enough of these, so I know that usually the derivative of that is going to be equal to that outside part. So then du is equal to cosine of x, and then dx. And so that means that dx is equal to du over cosine of x. Now I substitute my things back. So now I'm going to have the, and you know what? Before I do that, I might as well change my bounds. So I'm going to change my bounds. So if we're going from x equals 0, well, if I plugged in 0 into that, sine of 0 is 0. So for x equals 0, my u is also going to be 0. And then for my x bound of pi over 2, my u bound is going to be, well, if I plugged in pi over 2 into my u function, that's going to be sine of pi over 2, which is 1. So those are my new bounds that I'm going to be working with. All right. So anyways, back to the substitution part. I'm going to have the integral from 0 to 1 of, let's see, so I have cosine of x, and then square root of sine of x. I'm just going to write that as u to the 1/2 power, right? Instead of saying square root of u, because sine of x is u, times, and then dx is now du over cosine of x, Cosine of x is canceled. And now I have the integral from 0 to 1 of u to the 1/2 du. Now I'm going to do my power rule, add 1 or add 2 over 2. So that's going to be u to the 3/2 divided by 3/2 is the same thing as multiplying by 2/3. Yeah, and that's going to be from 0 to 1. So when I'm going to plug in my upper bound, so that's going to be 2 times pretty much 1. So 2/3 minus, and if I plug in 0, that'll be 0 over 3. So then my final answer is 2/3. Okay. All right. Hopefully I didn't seem like I was rushing through that, but I'm kind of eager to get this video done. I'm kind of tired of recording. So now I'm going to go ahead and do this one. If I have, it makes sense to make my denominator, because the derivative of my denominator will equal that other portion of the function. So that's what I'm going to do. I'm going to set my u equal to x squared plus 4. Du is equal to 2x dx. I'm going to go ahead and change my bounds as well. I'll just do that here. I have some space. So my new bounds is going to be, sorry. I got to get dx by itself. Getting ahead of myself. I'm getting eager to finish the video, and then it's causing me to be sloppy here. So my bounds are going to be, so for my bound of 0, so my bound of x equals 0, my new u bound is going to end up being, if I plugged in 0 into this, it'll just be 4. And then for my x bound of e, if I plugged in e into my upper bound, then I'm going to have u is equal to e squared plus 4. It's not as pretty as I thought. Anyways, that's going to be annoying to work with. So whatever, let's just keep going. So then we're going to have the integral from my lower bound of 4, my upper bound of e squared plus 4. And now I'm going to go ahead and do my substitution. So I can't substitute anything into that. So that's just x. X squared plus 4 is u. I don't know why I drew an obnoxious line, but that's fine. Times du over 2x. Well, the x's cancel. So I'm good. I have no more x terms in my integral. So I'm going to, and then I have a 1/2 that I can pull out. So I have 1/2 times the integral from 4 of e squared plus 4. And then I have 1 over u du. And hopefully that you know what this integral is. So I'm going to have 1/2 natural log of, I'm going to leave that outside. So 1/2 natural log of u from 4 to e squared plus 4. All right. And then I'm going to go ahead and plug in my upper bound. So I'm going to have 1/2. My upper bound is natural log of e squared plus 4, and then minus my lower bound, natural log of 4. That's pretty much a good way to end the problem there if you want. I'm going to take it a step further. I recognize my log rules. If I'm subtracting 2 logs, then I'm dividing whatever's inside of them. So that's going to be 1/2 times the natural log of e squared plus 4 over 4. Are you going to remember your log rules? Probably not. Maybe that was a refresher. And if not, I'll accept that answer on the test. So there you go. I went over as many problems as I could for U substitution. I wanted to do that. Maybe I could have gone over half of them and you would have been okay. But I still feel like, U substitution is such a common integration technique used by so many different calculus professors, and I would bet that it's going to be asked quite a bit on the AP exam. So it's definitely worth going over in detail. So I gave you guys plenty of problems to work through on the problem set. If I could do these 10 problems in 30 minutes, then, you can probably get through that problem set in an hour or two. I think, especially if you really sit down and commit yourself to it, because I also did a lot of explaining while I was going through these. So hopefully this was helpful. If you have any questions, of course, you can always ask me, and I'll leave you guys to it. Take care.